Welcome to section 1.4, day 1, increasing, decreasing, and extrema for functions. Today's objective is to determine intervals where functions are increasing, decreasing, and constant, and to determine maxima and minima of functions. So first off, increasing and decreasing behavior graphically. When we look at a graph, we can analyze it, and we can include a description of where the function is increasing, decreasing, or constant. This graph has all three things happening. And if we look at our graph, we are increasing as we come in from negative infinity all the way till negative 3. So if we're doing notation, we are increasing from negative infinity all the way until negative 3. We are constant on the interval from negative 3 all the way to positive 2. From that distance, we're staying at positive 4 the entire time for our y value. And then we are decreasing when we get past 2, so our interval is from 2 all the way to infinity, because we have the arrows on the ends. When we write intervals for increasing, decreasing, and constant, we do need to use the parentheses around it for the intervals. We do not actually include the place where it changes from increasing and decreasing or from increasing to constant. That's why we use the parentheses. So we can describe our increasing, decreasing, and constant behavior algebraically. So there's a lot written on here, and it says increasing on an interval if and only if for any 2 points on the interval, a positive change in x results in a positive change in f of x. So what does that mean? Is as we go from left to right, our x's are increasing. If our y values are getting higher, going more positive, we are increasing. Sort of makes sense. Decreasing is sort of the same idea from left to right. As our x's go up, our y values should go down. And for constant, as we go across our graph from left to right, our x is increasing and our y stays the same. Sort of makes sense when you look at it, when you think about it. This is what it looks like algebraically. This is a notation that you'll see in your book. So analyzing graph behavior, estimate the intervals on which the function is increasing, decreasing, or constant. And then it says the big piece right here, support your answer numerically. When it says to support your answer numerically, you'll need to show what's happening using a table so here we have analyzing graph behavior. We want to estimate the intervals on which the function is increasing, decreasing, or constant. And the key part with this one is it says support your answer numerically. So when you look at this graph, you might think that as we get to 0, we get a flat spot. So you might think there's a constant area in there where it's not changing. But if you look at our table over here on the right, to make sure what's going on is I actually look at a table of values going across my graph. I see there's a spot that might be flat. So I look at what's going on around 0, and you'll see as we get close to 0 at negative 0.5, we're at 0.25. At negative 0.2, we're at 0.016. 0 goes to 0, and then we go to negative 0.016 when we get to 0.2. So for the entire domain of this function here, we are going down from left to right. So we are decreasing on the interval from negative infinity to infinity. We are decreasing the entire function. When it says to support your answer numerically, like this one looks like it could have a flat spot. Show me some numbers that proves that it's not. Right here shows me it is not. I included more numbers on my table, but if you give me those three that show that it is actually going steadily down from left to right as we go through the origin, it shows that this is not a flat spot, that we are actually decreasing the entire time. And that is how you're supporting your answer numerically. All right, here we have another function. We're going to do the same thing. We're going to analyze it, look for increasing, decreasing, or constants. So first, let's look for increasing. By looking at the graph, it looks like we are increasing until we get from negative infinity to negative 1. And it looks like we're increasing from 1 to infinity, because we are going uphill as we go from left to right on our graph. So to support this numerically, what we want to see is what's happening around negative 1. So here's negative 1 on my table, and it shows that at negative 1.5, we're at 1.125. Then we are going up to get to 2. When we get on the other side of negative 1, we are back at 1.375. this table shows that at -1 we have a high point. So we increase until we get to -1 and we start going back down. And this is our support that we get numerically. We show it's increasing until we get to -1 and then it goes back down. So we are increasing, I'll just use INC, and we're increasing from -infinity on our X, that's not a very good infinity symbol, all the way to -1. All right, then we have a second place that we are increasing, and that starts right here, and we start going back uphill again. And this is happening when X is 1, is what it looks like. So again, we use our table, see what's happening around 1. As we get to 1 is at -2, and then you see that at 1.5, we are at -1.125, which is higher than it. When you're on the other side of +1, you'll see that at 0.5, we are at -1.375. So it shows that we're going down, we get to a low point right here, and we start going back uphill. So we have two places where it's increasing. We're also increasing from +1 to infinity. And again, this is how we're going to show it numerically. Now we're going to do the same thing for decreasing. And you will notice when we do a few of these that our decreasing is going to use the same endpoints basically as what our increasing has. So here we're going downhill from here, if it lets me write, going downhill from, looks like from -1 to 1, which is between our two increasing intervals. And again, the way we show this, and if you give me this table, it shows me enough. When you look at the table, let me erase what's on here already. So for the increasing part, you'll see a different piece. For the decreasing piece here, we have -1 to 1. You'll see from -1, we start at 2, we go down to 1.375, then 0, then -1.375, down to -2, and then we start going back up. So we're showing that we are decreasing this entire time from -1 to 1. I do not need all the numbers in here. What I would like to see though is at least one number between your peak and your valley. So give me at least one of these numbers in between the peak and the valley. It shows you that you're steadily going down from left to right. Here we have another graph. We're going to look for increasing, decreasing, or constants. Again, we have to justify our conclusions numerically. So that's why I have this table. And when we look at this graph, it looks like we are increasing until we get to around -3.1, and that we are constant from -3.1 going forward to the right on the x-axis. So we have to show this numerically again. So I'm saying that we are increasing from -infinity to -3.1. And this table is showing me this. With these two numbers here, I am showing you that I am going up, because at -3.2 we're at 1.4, and -3.1 we're at 1.7. So I'm showing that we are increasing until we get to -3.1. We are then constant. We look at -3.1 is at 1.7, then -3 is at 1.7, -2 is at 1.7, and so from -3.1 to infinity, we are a constant 1.7. For this, give me, again, some points that show we are constant. -3.1 and -3 would be enough, or you give me -3.1 and -2. Show me that we have a constant value coming back for our f of x, or our y value. All right, that's enough for increasing, decreasing, and constant. Now we're going to look at extrema. So critical points and extrema. Critical points are a very key concept, especially if you go into calculus. So critical points are points where a tangent line to the function graph is horizontal or vertical. So you're looking for tangent lines, horizontal lines right here, and then it's harder to see them on there for the verticals. The horizontals are easier to see. We are going to mainly work with horizontals right now, but critical points also happen when you have verticals. Extrema. This is where critical points where the function behavior changes between increasing to decreasing or decreasing to increasing. This is the top of your hills, the bottom of your valleys. And the extrema are either maximums or minimums. We're going to go a little more on that on the next slides. An inflection point is a critical point where the shape of the graph changes. This is where you have your vertical tangent lines. These are hard to see, but this changes concavity. We aren't going to get into concavity right now, but I wanted to show you this because critical points happen for Extrema and where inflection points happen. We'll hopefully get to that later this year. Today we are going to focus on the Extrema part, where we have horizontal tangent lines. So here we're going to look at relative and absolute maximums. Relative and absolute maximums happen at the tops of hills. So the relative maximum is the greatest value f of x attains on some interval of the domain. And the absolute maximum is the greatest value f of x attains on the entire domain. What we're looking at here is these high points. So if you look at right around where -1.5 is, it goes up to just above 2. That y value there is higher than all the other y values around it, so it is a relative max. When you look at the other one I circled, at roughly a little over 1 and up to 3, this is also a relative max because it's higher than all the stuff around it. But in this case, this relative max is also the highest point for the entire graph. If you look at the ends of our graphs, it has arrows pointing down, means they go on to negative infinity. So this is the highest y value the graph attains. So this relative max is also an absolute max. It is the highest y value of the graph. So if I ask for relative maxes, you have to include your absolute max in there because it is also a relative max. And that's why I'm showing you this. All right, let's do relative mins and absolute mins next. This is the same idea for relative and absolute minimums as for maximums, but now we're looking for the low points. And the relative minimum is the least value f of x attains on some interval of the domain. And the absolute minimum is the least value f of x attains on the entire domain. So again, we look at our low points. We have a low point here. We have a low point here for what's surrounding it. So roughly at -1.5, -2, we have a low point. That y value is lower than everything around it, so it is a relative min. When you get over to 1, let's say 1.1 and -3, this is also a relative min because it is lower than everything around it. At the same time, this is also the lowest point on this entire graph, so this is also an absolute min. It is both a relative and an absolute. Just like we did with increasing and decreasing, you will have to do this and show it numerically, and that is what we're going to do next. All right, so here it says to estimate and find the extrema of the function and support our answers numerically. All right, I already have a table set up here for you. I built this using my calculator. When you do this, you're going to be given a function. I recommend you type it in your calculator to graph it and use it to find and look at your graph and see where you can find your mins and maxes. And you can calculate that on your calculator by hitting second calculate. If you do not know how to do that, please let me know. And when you do that second calculate, you're looking for mins and maxes. But when you're looking at the graph like this, we're looking for mins and maxes. We're looking for horizontal tangents. So if you look at this graph, we have a horizontal tangent right here at -1. We have another horizontal tangent here at 0. Another one right here, roughly at like 0.7 or so. And another one right here. We can draw horizontal tangents to our curves in those 4 locations. Those are all critical points. When I did this on my calculator, like I said, I looked for the mins and maxes. It tells me where these critical points are. One of our critical points is at -1, +2, like it shows in my table. We'll talk about that more in a minute. Then we have another one at 0, 0. Then my next one is at 0.659, and the y coordinate is 0.4775. I'm running out of room here. It's a bad looking 7. And then I have one more at -1.9. -4.191. So I have 4 critical points. At these critical points is where we can have things change from increasing to decreasing or decreasing to increasing. I got all my x values using my calculate function on my calculator when I graphed it. All right, now we're looking for relative mins. And again, we did this earlier with increasing, decreasing. Now we're looking for minimums, so I want to see what happens at my minimums. We have a relative minimum at 0, 0. And how I show this numerically is I give you the points, something to the left and right, relatively close to 0, 0. And you'll see that at negative 0.1, we're at 0.0318. Then we go down to 0 at 0, and then we have at 0.1, we're at, again, a little bit higher than 0 at 0.0278. It shows that 0 is lower than the stuff on left and right of it, so we have a low point at 0, 0. We have another low point when we get to 1.9 and negative 4.191. Again, we look at a table. I use a step of 0.1. I show a point before it, a point after, 1.9, and you'll see that we have negative 4.044. It goes down to negative 4.191 and then back up to negative 4. This demonstrates that 1.9 is lower than the parts around it. Then we look at our absolute minimums. Well, if you look at this graph, we have this going on to negative infinity. So we do not have an absolute min. There is none. Because we have an arrow and it shows it keeps going down to negative infinity, so we do not have an absolute min. Then we look at a relative maximums. We're looking at the tops of our hills, and again, when I did my calculations, I found that negative 1 goes to 2. And again, I give you points around it to show that is indeed the top of a hill. Look at these three, you'll see we have from 1.753, then it goes to 2, then back down to 1.985. We look at our other relative maximum, which is at 0.659, and the y coordinate is 0.4775. All right, and again, I show you at 0.6 what's happening, and what's happening at 0.7. You can see that 0.4775 is a little bit higher than those around it. This is, again, supporting it numerically. Looking at absolute maximums, and again, we do not have an absolute maximum because we have the arrow here, and we have things that are higher than 0.47, actually higher than 2. So there is no absolute max. Most of the graphs you guys do today will not have this many turning points in them. You only have a couple of mins or maxes, but this is what you need to do to show it numerically. Calculate the mins and maxes using your calculator to find out what those x values are, then build your table off of that. All right, here's our last slide of the day. Here we have the function f of x is 3x to the 4th plus 3x cubed minus 4x squared. And again, we're looking for critical points, relative mins, maxes, and absolutes. Again, plug these in your calculator, find out where these mins and maxes are, and then use a table to justify numerically what's going on. So critical points, we're looking again for those horizontal tangents, and here's a horizontal tangent, here's a horizontal tangent, and here's a horizontal tangent. And when I did this on my calculator, I found out that my mins was at negative 1.27. I had another min at 0.523. That's what I found on my calculator. And then when I did a table, I found these two values around, both of these, to show you that we are indeed going down and then back up. And that's my justification numerically. So my critical points for mins, anyway, were at negative 1.27, comma, negative 4.793. We had the other min was at 0.523, comma, negative 0.440. This is hard to write with today. And then we have a third one, which is at 0, 0. That's our maximum. That's another critical point. So we have 3 critical points. Then we're looking for relative mins. Where are the low points on our graph? Well, our low points are right here and right here. And this is what's going to show that numerically. I'm giving you my critical point, and then I'm giving you something to the left and to the right of it. And it demonstrates that we are indeed going down, and we have a low point at negative 1.27 and one at 0.523. So our relative minimums are at negative 1.27, comma, negative 4.793. And our other one is at 0.523, comma, negative 0.440. Those are my relative mins. Then we look for absolute minimum. Is there a place that is the lowest point on this graph? And in this case, we do have it because we have, our ends are both going to infinity. So we do have an absolute min, and it is at negative 1.27, comma, negative 4.793. So that's our minimums. Then we're looking for relative maximums. We have one high point that's relative to all the rest of it, and that is at 0, 0. Again, I show you where 0, 0 is, and I show you what's going on around it. At negative 0.1 and 0.1. And we show you those are lower than at 0, 0. So we have a relative max at 0, 0. Since our graph is going off to infinities, there is no relative max. That is all for today. Today we went through finding increasing, decreasing, and constant. That is always written in interval notation. And we use parentheses because the endpoints are not included with the increasing, decreasing, and constant. And then we did relative and absolute minimums and maximums and critical points. We always give those as ordered pairs. They are points. Thank you for watching and have a nice day.